Okay, we start up with the final part in this course, turbulence, and today the topic will be direct numerical simulation. Also, we will round off the course with verification and validation. Very important concepts, something that we really have to take with us. But for now, we start, or continuing actually, with turbulence. Now, before we jump into DNS and LAS, we have a peek of law of the wall. This is something you should be very familiar with. We can take any of these. Maybe even better to take the Wikipedia. Here we are. So I will talk a little bit about this one. It's something basic within turbulence that you definitely have to be aware. So we start today the law of the wall. The idea is as follows, that close to a wall it should be possible to predict turbulent behavior. If you sort of say that the turbulence is going to be produced close to the wall, fair enough, but it should then also be destroyed in the same location. You don't have much of a transport effects close to a wall. And yes, indeed, that might be the case. So if you look at a log-log plot here of the non-dimensional velocity, so you have, what do they use? U plus, which then will be your real velocity, and then you scale it against something called either U star or U tau or something. U tau they used here, where we can use U tau as well. Sort of, it's called a skin friction velocity. It's actually not a velocity. It's based on the wall shear stress divided by the density. So it's a velocity scale based on actually the friction force close to a wall. The Y plus, that's a dimensionless length, and as you can see there, it will be equal to the real dimension in meters, and then you multiply with this wall shear stress or the skin friction velocity, and then you divide by viscosity. So you can actually see there you have length velocity over viscosity, sort of a Reynolds number. And plot any measurements in the lab, velocity along a flat plate. You will have then some region that will be something like this. You will here have first U plus equals Y plus. So these two will be in balance. And then you see, if you start inserting here, the real velocity, U tau equals Y U tau viscosity. Okay, the velocity will be equal Y multiply with, and then you have this U tau squared. Then you get the wall shear stress tau, and you will have actually the dynamic viscosity. And this one, if you start inserting numbers, you will see is the laminar solution. This is the laminar parabola. So the velocity goes as y square if you start inserting symbols here. And that one has given the name of this innermost layer very close to a wall, some y plus equals 10 or smaller, very, very close to a wall. People believe that, okay, here the flow is roughly laminar, because on average, the velocity profile tends towards this laminar parabolic solution. And yes, that's true, but that's definitely not the entire truth. If you look at a real wall and a real turbulent flow, here you have the laminar parabola. We are now very, very close to a wall. If you look at how the turbulent velocity snapshot actually looks, it will look very something like this. Further out, it will still be turbulent, but then the action is not so strong. It's very, very close to the wall, all the action takes place. That's where you produce the turbulence. So yes, we call it the laminar parabola, a laminar solution, or even a viscous sublayer, many names of this innermost layer. Viscous sublayer they use here. People have sort of the imagination that, oh, it's laminar in there. That's a very big lie. That's actually where all the turbulent action takes place. It's really violent. But on average, yes, you get this one here. Going further out, okay, then you can have this log connection, straight line in a log plot. So there you will have this equation here, u plus equals something log y plus. And then you have to combine these two. So people are using this law of the wall a lot because it's sort of universal. Yes, this will be the behavior very close to a wall for a turbulent flow, that's true. But don't remember what is really happening. Very violent behavior very close to a wall. Very violent indeed. How close are we talking? This plus unit in distance, okay, you have to insert numbers to find how many meters are we talking, or actually millimeters typically. You can also say that this will roughly equal what is called an eta, which is then the length scale of the smallest turbulent motion. It's called a Kolmogorov microscale. So it's a length scale, and one Kolmogorov is around 1 plus unit, roughly. It's not perfect, but nearly there. I think you can even find Kolmogorov here as well, if we look at it. Kolmogorov length scale. So it's a dimensional analysis solution, how to find the length, a length scale. So there you see the Kolmogorov length scale, eta. It's of the order the viscosity divided by an epsilon, viscosity over a dissipation, and then to the power of 1/4. Something like that. Yeah, you have some other versions of it as well. I won't go through all this in detail. It's more for the interested parties. You can have a peek. A lot of material for this these scales if necessary, but they're going to be important now when we are talking about DNS, because we are going to resolve everything with a direct numerical simulation. I need to resolve all the scales all the way down to a Kolmogorov scale. We are going to have control over everything that's happening. That means if you have a length scale here in a domain between, say, a pipe or in between two plates, whatever, you have a length scale here, and you have to resolve it. How many cells do you need? Well, the number of cells will be something like your length scale divided by this Kolmogorov length scale. And remember, by nature, turbulence is three-dimensional. So even if you like it or not, doesn't matter. You're going to need this in 3 dimensions. And it can be shown then that this will be roughly the same as your Reynolds number to the power of 9/4. And there is the price we have to pay if we want to do a DNS. You have to resolve everything all the way down to Kolmogorov. This is the amount of cells you are going to need. You have the Reynolds number. The bulk Reynolds number is, if it's a turbulent pipe flow, 2,300. That's the lowest one possible, just turbulent. And then to the power of 9/4. You quite rapidly get a very, very big number, and you will blow the memory on any computer. So this is sort of the pain that we are looking at for solving a DNS problem. We are going to cheat. We have to cheat. And the way we are going to cheat is to say that a little outside of the wall, past this viscous sublayer, sort of in the log area and even beyond, then the turbulence is not so intense anymore. It's still turbulent, but it's not so violently as you find very, very close to the walls. Meaning up here, you could have length scales, say about 10 Kolmogorovs, and you will still capture the absolute major activity. So yes, okay, we can cheat a little bit here. On the other side, getting very, very close to the wall, then actually we are going to need down here, your smallest cell should actually be 0.1 Kolmogorov, 1/10 of the Kolmogorov. You really have to resolve this layer very, very close to the walls. That's unavoidable. That's where all the action takes place. That's where the turbulence is born. Of course, you need control. So very, very small cells down here. Another way we can cheat is the other dimensions. I mean, here we have the direction perpendicular to the wall. If you look at the direction in the streamwise or the spanwise direction, then you can definitely use bigger length scales. So the cell closest to the wall, he is extremely thin, but he can be pretty wide. That's okay. So some 10 Kolmogorovs in both directions, that should be okay. So, but still, very, very big number. Very big number. Let's go into the home page. And in the material you have been given, we have been through turbulence 1. We have started turbulence 2. We are missing the final part there about DNS. before I take that one, I want to have a peek into this article, Numerical Transition to Turbulence. So you get an idea what the DNS actually is. So it's not my most important work, but it was a quite fun problem actually. So now the DNS that I did in those years, it was early 80s actually. We had the supercomputer at that time. They were called Cray machines. So Seymour Cray, he was creating very big, very fast computers, but they typically had very few CPUs. So expensive, very expensive. We bought one here in the university. It costed 100 million crowns. And the laptop you have today is about the same speed. 100 million. And it was very big. We have the YMP. They are using it as a bench in the lecture building, so you can have a look at it. And you have the Cray 2 machine, even more advanced. That was water cooled. It was really, really fancy machine. Anyway, that was our option in those days. So yes, we had the possibility to do a DNS. And the problem here, we need the geometry actually. Yeah, we can take it here. As an example for a DNS, channel flow, which is then, well actually it's a one-dimensional problem. You have one plate here, you have another plate down here, and then you send in a flow. You have a pressure difference, so of course you will have the flow running, and if it's fully developed flow, you will get an average turbulent velocity profile looking something like this. And that was the aim. We wanted to do a DNS of this simulation. One-dimensional problem. I mean, this is the most trivial geometry you can find. So the Reynolds number here should be around 3000. So it's just turbulent. And the reason that we then keep it so low, just turbulent, was just because of the resolution. Because for doing such a simulation, you still have to do it three-dimensional, like this. Although you're only interested in a one-dimensional solution, you still have to simulate a three-dimensional case. Because the turbulent by nature is three-dimensional. And it's transient. You can't do a steady-state simulation. You have to let things change with time as well. So I run this using 4 million grid points, roughly, which was then almost the limit for the memory on the computer in those days. And now the problem is as follows: the boundary conditions. How can we create a boundary condition here? I want a fully developed turbulent flow. So that means you can't send in a flat velocity profile and let the flow develop into a fully turbulent flow. Well, you could, but you will take forever to achieve a correct solution. You have something called an entrance length, which then is going to be pretty long. Several, not diameters, but several of this h distance before it's fully developed. And we were not interested in the development, we were interested in a fully developed, steady-state, averaged turbulent flow. So the problem is how to achieve it. So what you do, you take as an inlet condition whatever comes out here. So you use cyclic boundary conditions. So a velocity going out here, you just send him in on the other side, and vice versa. Same goes with the pressure, except then in the streamwise direction, you need then sort of a driving force in the problem. You need a constant, it could be gravity for that matter. You need a constant term to have a force pushing the fluid through. Same goes now in the spanwise direction. So you have to choose a width into the in the spanwise direction, appropriate width. How big should that be? That's another story, coming back to that. And then you use cyclic boundary conditions here as well, because you can't just keep it open. That's not really physically. So whatever comes out here, you send in on the other side, and vice versa. Sort of a cross-coupling there. So cyclic boundary conditions in both streamwise and the spanwise direction. The normal direction, there you have solid walls, so not a problem there with any boundary conditions. And then you start to simulate. And you have a transient full three-dimensional simulation. And the first attempt that I did was just to say everything was zero, and then you sort of set up a driving force, and then you just let the flow evolve. And when I did that, I wasted I don't know how many thousand CPU hours, and I got a laminar solution. Although the Reynolds number was turbulent. But remember, a laminar solution is still a solution of the Navier-Stokes. It just should be unstable. So if anybody has sort of slammed the door or shaking him a little bit, he should trip and become turbulent. But he didn't by himself, so I had to help him. So the next attempt, I sent in sort of an initial field where you have here just some empirical turbulent-like velocity profile together with a random generator. So I just used totally white noise superimposed with this averaged velocity profile. Now, if you look at a problem, the answers that I want in the end, they will be one-dimensional. So that means for one single plane, somewhere, say here, one single plane, you have a lot of velocities, but you can then average all of them and find one single velocity to sort of represent the velocity in that plane. So you can do averaging in every plane here in the Z direction from wall to wall. I think I used Z, yes. So you have X, Z, and Y. So this is sort of the problem with the DNS. You get a tremendous amount of data back, but in the end, you may want just a acute velocity, one-dimensional velocity profile. You need to get good statistics. That is the problem here. Finding good average results. So the mean velocity profile, if you look at the different averaging here, that wasn't the mean field, this was the velocity squared. So looking at the one to the right, that is the initial field along one single straight line somewhere inside the domain. It doesn't really matter where, but from solid wall to solid wall. So you see totally random, a lot of noise, really violent. And then you do an average, then you'll see, you will find the first one there, that's just an average over a single line, and then finally over an entire plane. And for the intensities, they should look something like this to the left. That would be sort of a good average. But to achieve it, you need many examples. So, and this is also something you should keep in the back of your head. We say with the DNS, we resolve everything. We just solve the Navier-Stokes in detail all the way down to Kolmogorov, more or less. So that people then can imagine that you are simulating here a channel flow, meaning if you drop a feather somewhere in the beginning here, then you could trace that feather exactly, how he moves and where he will exit on the other end. No, that's not possible. You are going to deal with discretization error. You need tens of thousands of time step. Of course, you're going to accumulate errors. So no, you can't really do this. You can't say that you have everything correct. No. But with the DNS, you can sort of look upon it as a whole bunch of different solutions of the Navier-Stokes. A whole bunch of them. And you need many. And then you can create good average, create good statistical results. So you have many solutions of the Navier-Stokes. That's what we are interested in here. And to the left there I have averaged over the planes, since they have the same conditions, and also I have averaged over time. So the one to the right, that's only I think it's a line integral. The mid, that's the plane integral, and to the left also several in time as well. So to achieve good statistics, you have to do many time steps as well. You can't just rely on one single solution here. So you need a lot of sampling, as we called it, a lot of averaging, many solutions of the Navier-Stokes. Now, initially, as I said here, you have a lot of noise. So I used a random generator. And of course, only during the first time step, just by the continuity equation, he was filtering out a lot of this noise because it was totally unphysical, nothing real at all. So that was the problem now, how to achieve sort of the correct correlations, turbulent correlations in time and space. So what I did was to have a look at the turbulent kinetic energy, which then is UI, flux, averaged, sort of the sum of all these intensities. U flux square plus V flux square plus W flux square. And then you can create sort of a turbulent kinetic intensity or energy, if you like. This now being one single point. What I can do here is taking a total average. I don't know how I wrote this. I think I did something like that. Sort of an average of the entire volume, a total volume average. So that means you sum up all these in every cell and then create a sort of a volume average. And then I looked at that quantity, the total kinetic energy for my entire volume. And I plotted that one as a function of time. Total kinetic, turbulent kinetic energy. Due to this initially totally rubbish starting field, random, he was sky high initially. Totally unphysical, but very high. And during the first time step, he almost dropped to zero. And then he was down here somewhere, very close to zero. And then I got afraid that he will die out and I will get just the laminar solution. But then luckily he built up and then he started to go too high. Then I was afraid he should explode. But luckily he changed his mind and then finally settled on a steady level. So from here I could say now I have fully developed turbulent flow. And it took many hours to get it, CPU hours. And in those days, one CPU hour, and that was 20,000 crowns, so that was expensive. So here actually is the different, not volume integral, but the averaged from wall to wall, but here as a function of time, because the intensity, they should look something like this. Peak close to the wall, close to zero in the center, and then a peak on the other side. So here it was fun to see then, as a function of time, he actually tripped and established the turbulence on one side before the other. That's just, of course, due to numerical noise, so nothing to do with physics. So here, with respect to time, initially you have something totally unphysical, but then through the Navier-Stokes, he sort of organizes himself, establishes a correct turbulent field, and then somewhere along the line you start saying that, okay, now this is a good representation of the real physics. Start with something totally rubbish, and then sooner or later, hopefully, you will obtain correct turbulent field.
May I ask, you talk about the intensity?
Yeah.
How do you define this?
Intensities, they are the different U-flocked square, V-flocked square, W-flocked square. The Reynolds stresses, but only the, say, the normal component in the matrix. For the shear, you will have UV. That will be the Reynolds shear stress. These will be the normal stresses or intensities. People call them also intensities. But they are, as you see, element of the turbulent kinetic energy. But turbulent motion only. Looking at the velocity profile, how he sort of developed, well, that was sort of the initial state. That was the averaged turbulent velocity profile that I gave him from this empirical formula. But you see here the shear stress, it's fairly close to zero. So on average, I didn't have any real turbulence. It was just noise initially. So that was not so promising. And if you look at the three different intensities from wall to wall, the normal components, they were very, very small indeed. And then I started simulate in time, and all of a sudden he tripped on one side first and then the other afterwards. You see the velocity profile, he tends from this turbulent-like shape. It's not, you can actually see it from the velocity profile. The Reynolds number is not so high. I mean, if this is flow between two parallel plates, if it's very turbulent indeed, then you have zero on the wall, then you have a rather flat profile. That's very turbulent. If the Reynolds number is just turbulent, then the shoulders will be a little bit more something like that. Still not a parabola by all means, but the higher the Reynolds number, the stronger, the sharper shoulders, you might say, on the velocity profile. So you can tell from the initial one that, not that high Reynolds number, which was okay. But now look at the development. He tends towards the parabola, clearly. So closer and closer to the laminar solution, which I was not interested in. But luckily, he starts now developing real turbulent flow. But he started to the left wall first. And there also you see the shear stress now starts to build up. And here the intensity gets very high. And then also you start getting more a turbulent-like shoulder to the left here. More and more. And then luckily also on the other side as well. And then in the end, he developed quite nicely to to a fairly decent turbulent velocity profile.
So only the normal stress is called intensity. The shear stress is not.
Yeah, we don't call that one. That's not an intensity. You just call it a shear stress, yeah, or Reynolds shear stress. Yeah. So here you have the different intensities as a function of time. So I had to do many here non-dimensional time units. One time unit here was actually the time it took from the average velocity to go from an inlet to an outlet. And that was many thousand time steps. So it was expensive to sort of build up a correct steady state level here and finally say that yes, now I have a fully developed turbulent flow. So it's expensive actually to just get things started. And from here on I could now start achieving statistical results to getting an answer to my problem. But it was not just switch on the on button here. That I can show you. Wow. The wall shear stress, or here the skin friction velocity, that was something to do with the wall shear stress. And now remember this problem here. You have given the driving force in the problem. You know, say, the pressure difference. So you have a pressure 1 here, pressure 2 on the other side over a length L. Then you know the pressure gradient. That's sort of given externally. Then when you do a control volume analysis, put a control volume inside the entire domain, what do you get? Well, you will have the pressure difference, P1 of course bigger than P2. He will then have to be multiplied with the height and the width. So he is H high, and the width here inside the blackboard is B. So there you have one force, has to balance exactly the wall shear stress multiplied with the plates, and they were L and they were B, and I had 2 of them. So from that equation you can see before you begin, you know what the wall shear stress should be. You can calculate him in advance because this is externally given as a driving force. So you know the wall shear stress. What you don't know is how big is the average velocity going to be. That's unknown. But then, since you have sort of the sum of forces equals 0, you don't have any mean acceleration in this problem. It's a steady state problem. So then, of course, the sum of forces has to be completed. Then I should have a wall shear stress that should be equal to 1 on both sides. So that was sort of another monitor value I could check. When do I have the force balance fulfilled? And yes, indeed, they were tending towards 1, but again, I had to simulate for a long time to obtain it. So this is also a sort of a headache when you are doing these simulations. When do you know that you have a solution? When do you know? This was actually a very good monitor, the volume averaged kinetic energy, turbulent kinetic energy. When he was sort of leveling off, then okay, now I'm fairly safe. This force balance, that was another monitor I could use. Control volume analysis for the entire domain. Yeah. So here I did then After 30 time units, I could then start taking samples, achieving good statistics for finally obtaining any answers to this simulation. As we discussed earlier, I think I mentioned it when we talked about multigrid. What you really want here is good answers, like you have everything, you know everything, but in the end here I was interested in things like the velocity as a function of z only. Not with time, not with x, and not with y. So I want some good average statistics to get him rather correct. You could do the averaging for each plane for one single time level. Yes, that was okay. But it still wasn't really good enough to have a nice and smooth solution. So you have to simulate in time and say, here, you take a snapshot of the solution. There you have one solution of the Navier-Stokes, and you can create the averaging in x and y directions, okay. But then the velocity profile wasn't so smooth. Then you simulate further, and here you do another sample. And then it's not any idea, it's not worth the effort to take every time step, because you have very small changes from one time step to the next. So the solutions of the Navier-Stokes then are going to be quite similar, highly correlated. So you have to wait until, say, 100 or 1,000 time steps before you do another sample. Then you have a totally different solution. They must be uncorrelated, or else the statistics won't be worth anything. So you need different solutions. And then you needed many of them. And of course, the more you need, more expensive it's going to be. You have to simulate very, very long time. So you can imagine if you have a real full 3D problem, you don't have a one-dimensional problem like this one from wall to wall. You have, say, a flow over a car or something. You can't do averaging in space at all. Then the only averaging you can do is in time. Okay, then you need many, many, many time steps to get good average statistics. That is sort of the main problem here. So in the end here, I got very nice results. I was quite happy with these. And here, I could then go to the people doing experiments, measuring, and of course I could then say to these guys, sorry, you have measured it wrong. I have the correct answer. So we had some interesting discussions, I can assure you. So of course, I don't believe it until I see it numerically. Experiments, nothing to do with real life. Okay, we take a break.